Now I'm recording. Now I'm recording. Okay. But I wasn't done. Like, I haven't graded it all yet. And honestly, most of you haven't finished it yet. It's so much easier to grade a test if you guys finish it. Weird. Yeah. Okay, less talk, more listen. Don't make me yell at you. You're perfect usually. That's better. Davis, how many bruises from the other night? Everywhere?
I've got one really big one on my knee.
Yeah.
Oh, right there. Oh, that's not that great.
I saw you on the ice more like this than like this. It's okay though. His date was amazing. Who was his date? Oh, it was you. Okay. Hey, scan that QR code, would you? All right, where did that take you? Quizlet, to your vocabulary terms. Everyone, you will be tested on vocabulary. I don't ever do that, but I am doing it on chapter 11. Did everyone hear me and understand? You will be tested on the vocabulary. Did you hear that? Okay. All right. So make sure you start studying them. Make your own flashcards or do whatever. There are some words you have heard, some words you've probably never heard. All right. We ready to dive in? Okay. That'll be on the test, probably a practice quiz too. And they're tricky. So if I were you, I would invest some time. Okay, we're gonna start chapter 11, which is on what we call intermolecular forces. Intermolecular forces. If you need to know how to spell it, turns out that's a vocabulary term. Well, I wouldn't write them all down. That's what you just scan. But this is this whole chapter is about intermolecular forces. So I kind of have them right here. You can try and write them down if you feel like it. An intermolecular force is a force between like molecules. Now, it's easiest, I'll draw out a picture in a second to understand what an intermolecular force is. In chemistry, we have intermolecular forces and intramolecular forces. Just like if you're a nerd, you know there is an internet and an intranet. If I only got one kid nodding right now. If you're a driving nerd, you know there are interstates and intrastates. Yep. All right. Now, it doesn't matter that you didn't know the other two terms, but this is what matters. I have a water molecule that has a covalent bond between oxygen and hydrogen. This covalent bond is a intramolecular force. The force of attraction between the O and the H, because of their shared pair of electrons, constitutes an intramolecular force. It's an attractive force within or inside the molecule itself. So an intranet, which hardly anyone knows, Meyer knew, an intranet. If the internet goes down at this school, I can still email Mr. Miller because our computers are connected on an intranet inside the district. An internet connects you to the whole world. It's on the outside. An interstate is a freeway that goes all over the country. An intrastate is a state highway that's on the inside of my state. So an intramolecular force is a bond. When we've been talking about bonds, we've been talking about intra. This felt like a DJ. Waka, waka. Okay. Sorry, I'm weird. All right, now you may be aware that a water molecule is actually attracted to another water molecule. Yep. Yep. This is an intermolecular force. Now, you've had enough science to probably know this has a name right here. What's this dash called? A hydrogen bond. Now, listen to me. This is not a bond. Everyone, look at me. Everybody, hydrogen bonds are not bonds. That's a great question. I can't answer that. It annoys me too. A hydrogen bond is a intermolecular force between, it's kind of complicated, a hydrogen that is bonded to a very electronegative atom that is also attracted to another molecule where hydrogen is bonded to an electronegative atom. That's the definition of a hydrogen bond, but it doesn't say bond, it's an attraction. You with me? Okay. Up here, I have some water. Okay. Here is water. My water broke. Sorry. Oh boy. And you guys thought that was an accident. Okay. This is a bunch of water molecules. Please look. This is an individual water molecule. All right, you got the other people can't see very well. Everyone say hello to my water. Here we go. Preset 2. Ooh, preset 3. Okay, well, if you're online, I'm like 1 inch tall anyway. So here we go. You can't see. What are they saying in the chat? All right. Let me open this up. Okay, hold on. Chat. Yes. Yeah. Thank you, Tim. I'm so glad I opened that up. Okay, here is an individual water molecule. The red represents what atom? Oxygen. The white represents hydrogen. The bond is like me trying to pull the white off the red. And it is possible, but it took a lot of effort. You with me? That is a covalent bond versus a hydrogen bond is when the negative part of the oxygen, I'm not doing a very good job here, is slightly attracted to the positive part of the hydrogen. So there's an attraction there, but it doesn't take very much energy to pull it apart. It takes some, but not very much compared to trying to pull the white off. Okay, bonds, really strong. Intermolecular forces, they matter, but not nearly as much as a bond. You with me? Okay, now let me zoom back out. We'll go to 1. Oh, my face was so good looking though. Ooh, that zoomed way out, but well. Okay, so that is an example of an intermolecular force. It's the attraction between like molecules. So 2 water molecules would be considered like molecules. They are the same. Now, intermolecular forces, they have an effect on the physical properties of substances, like melting point and boiling point, and the state of matter something is at its certain temperature. Like we know water is a liquid at room temperature, right? All right, right now it's a solid. Okay, I could kind of move it around and it becomes a liquid. All right, we know it's a liquid at room temperature. What happens if I add heat? All right, it becomes a gas. And I want you to think about what that really is now, what we're saying. And we'll come back to this, but think about what boiling really is. It's not the separation of H and O. Okay, that's definitely not what is happening. That would be breaking bonds. That happened in the Chernobyl accident. That's why it exploded everywhere. It got so hot, the O's and the H's separated, and then they combined again to make water and blew up the whole building. If that explosion didn't happen, it wouldn't have been that big of a deal. Okay, but in real boiling, we just got bubbles, right? They rise, and eventually we have steam. Steam is a gas, and gases have properties, right? In a gas, we would say if I had two molecules in a gas, how are they interacting with each other in a gas? They bounce. They really don't interact though, right? We said an ideal gas, there's no attraction. They're just completely inelastic things going on, minding their own business. In a perfect world. We okay with that? So in liquid, we have all these that are sort of together. And we know water is together because who's done a belly flop? It hurts. There's pain associated with a belly flop because you got to get your body all the way through all these attractions, right? And that takes energy or force. So in a liquid, there's some attraction between the molecules, right? When we turn it to a gas, there are no interactions. So by adding energy or heating it, we're separating all of these and making sure they have no interactions with each other anymore. All that work to do phase change. Go ahead. No, that's not what I'm saying. But thank you for clarifying. All right, we would now say this would behave like a gas. They're all separate, but that took energy, right? Okay, if these magnets were stronger, tell your partner the amount of energy it would take to separate them. Okay, no one said less because you're not dumb. It'd take more, right? Okay, so answer me this question. If my intermolecular force is high, what do I know about the boiling point? It's also high because it takes more heat to break it, or vice versa. If I have a very low intermolecular force, what state of matter am I most likely to be at room temperature? A gas. So in this room, talk to your partner for a minute and tell your partner what one thing in that has high intermolecular forces, one that maybe is medium, and one that is low. Have that conversation for a minute. All right, so here we go. What's an example of one that has high intermolecular forces? Your desk. Anything else? The metal, your phone, your chair, the floor. All those things are what at room temperature? Solids. Okay. Next, what one has medium? There's not a lot. Diet Coke, water, Ajax, the liquid soap. All right, your saliva, whatever. I don't know. Don't let me pinch your arm. All those things are liquids, which means there's some attraction between them. That's why they're in the liquid state, but they're not locked in because their attraction is so high. We'd call that a solid. All right, and then finally, we're all breathing air, oxygen, nitrogen, because it's a gas. It goes into our body. We have an exchange and we live because oxygen has a really low intermolecular force.
So when heat is added, it like the energy added just like makes it so the object, like the energy, the pull between the intermolecular force is just not as strong as the energy that they have. So
yeah. So what is happening inside on a microscopic scale is, just pretend we have like whatever this is and whatever this is, and they're just vibrating back and forth. And as soon as the vibrations get big enough that they can separate, then we've changed its state of matter. When it separates a little and just moves around, we call it a liquid. When we've broken every attractive force and it flies out on its own, then we call it a gas.
So that way, in places where it's warmer, it's like more humid,
Heat does help with humidity, but it's more their geographic location. They're by a water source. So that one's, well, I wouldn't say so humid. It's like 12% instead of 3%. But you go back east and the plane door opens and something assaults you. You're like, oh, we're in New York. What is this feeling? Like, I remember that feeling of humidity and cigarettes. Because when I was a kid, you could smoke anywhere, but not on an airplane. So you rolled into Newark, New Jersey, not technically, and they opened the door and it instantly like punched me in the face. Wanted to throw up. But then I lived back east for 2 years and I came home and my body was like I just cracked. It was I love the humidity now. I would rather live there than here, humidity wise. But they are related. All right. This is kind of nerdy, and we're not going to argue the existence of whatever or whatever. We're not Republicans or Democrats right now, but can we at least admit carbon dioxide has increased in the atmosphere over the last 200 years?
Yeah.
Okay, no one can deny that. No one can deny that. Okay, here's what's interesting. Global warming, or the temperature of the planet, is more dependent on the water in the atmosphere than is the carbon dioxide. So why don't we care about water vapor? Yeah, there's nothing we can do about it. And water and carbon dioxide have two way different things. When we get too much water vapor in the air, what happens? It falls out. Because water is attracted to itself. And if it cools or gets too much, they'll get close enough that they start to stick together. Whew. I'm like, no way is that going to go all the way through. They start to stick together and then they'll go through again and they didn't find anyone. Here we go. And they'll start to stick together. And eventually they'll get stuck together enough that they're too dense for a cloud to hold. And then it falls out. So the planet has an X amount of water vapor it can hold, and it will never get above it, or it falls out. Can we do that with carbon dioxide? No, it's an incompressible gas. So even though water really is more important, we can manage water. The planet does it itself. We can't manage CO2. Oh, thank you, Devin. I miss your beautiful face. All right. Anyway, kind of nerdy, but kind of interesting application to something in our world right now. Okay, I've talked a lot. Do we feel at least okay knowing what an intermolecular force is now. We went from never hearing the word to now hopefully understanding it's an attraction between things on the outside, not inside the molecule. Thumbs up. Okay, here we go. Yada, yada. Okay, okay, okay. So there's all sorts of these things and tons of them. Okay, line tool. The intermolecular forces affect them. Okay, you don't need to take a picture. They're the same things you scan. Okay, fine. All right, you can find this exact thing on Canvas if you feel like it. This chapter deals with intermolecular forces in liquids, solids, and gases. The majority of time will be spent on liquids. We mostly just spent an entire chapter on gases. Okay with that? It's governed by Pivner. All right, an ideal gas, really no attraction, doesn't occupy volume, all the collisions are inelastic, and yada, yada, yada. So, and there's what? And yep, solids are pretty boring. We will have a section on solids, but they're really just kind of boring. So we got liquids. All right, so here is more of just definitions. So we have intramolecular forces, and I already said this, but they are the attractive forces within molecules. These forces are generally referred to as covalent bonds. These forces give molecules their chemical properties. Now, these can happen in ionic substances, but we're mostly talking about liquids, and no real ionic substance is liquid at room temperature. So we're mostly talking about the covalent interaction between atoms when we talk about an intramolecular force. Right. Intermolecular forces are forces that exist between molecules. These forces determine the physical properties of liquids and solids. So you need to know the definition, and you also need to know that they are what determine the properties. Specifically, the melting point, boiling point, and the vapor pressure, which vapor pressure and boiling point are pretty similar. Are you guys paying attention or annoying me? I can't tell. Both? Okay, you're right. All right. So that's what those are. Now, this is an important concept right here to kind of understand. The physical state, meaning solid, liquid, or gas, of a substance depends on the balance of the kinetic energy, which is the temperature, of the molecules and the attractive forces between the molecules themselves. Okay, so there is some amount that everything's attracted, but we add temperature, which, remember, I described it as just having the two things. They're attracted to each other and they're vibrating. And if they vibrate or have a low temperature, if they don't vibrate too much, then they'll just kind of be here and they're a solid. But then I add more temperature and now all of a sudden there's an attraction, but they're not stuck. We call that a liquid. And I keep adding, and eventually they get so far apart, or so much energy, they move apart from each other. And I call that a gas. Okay. Now, this is super simple, and you would never think it might be on the AP test, but it can be on the AP test. It's a picture. Whoops. If you were going to draw a solid, how would you draw it? With circles. All right. You put them all together, like interacting with the, like touching. Okay. Right. All right. So a solid would look like this. Now that's 6th grade, but they could like ask you to explain, like, hey, it has a high density, and that's like 7th grade, maybe. All right. Or explain it's solid because currently the intermolecular forces are greater than the kinetic forces, meaning the temperature. It's a solid because the intermolecular forces are winning the battle right now. Okay? They have high IMF. IMF, you'll see that a lot now. It's the intermolecular forces, not the International Monetary Fund, which I know all of you thought, like, oh, the IMF, that's really important to our economic stability. I know, different class. Okay, then if you were going to draw a liquid, it's really hard to draw a liquid. So what's the only thing you really would do? Draw less of them. That's literally all you would have to do. Now, there still should be a lot of them, but the liquid would be less dense. You could, even if you felt like it, put like directional arrows on it. To, like, it's moving. You with me? And then really, you should know it has medium IMF. The attractive forces now are enough that they are still attracted to each other, but not strong enough that it prevents them from any movement. All right. And then your gas, probably super not hard to draw. Just draw a few things way far apart from each other. All right, we have our gas, and we would say it is a really low intermolecular force. In fact, when we assume it's ideal, we essentially say the intermolecular forces are zero, which is a lie, but they're really close to zero. Fair enough. TA, do your hands hurt yet? I'm right here. Okay. Oh, I like when I blend in. I'm almost 50, but I still blend in. Oh, never mind. So I do look 50. I thought I looked younger because I shaved a few days ago, cleaned up the eyebrows a little. All right, down to 210 today. Yeah, I'm feeling it. Feeling hungry. All right, we all right with the representation of solid, liquid, gas and the knowledge of high, medium, and low. Okay, now, if I have a substance, how do I change between a solid, liquid, and a gas? I add or remove heat. So I change the temperature, right? So it's a balance, the state, this is just all that's going to support the sentence we started with. The state of matter is dependent on the balance between the temperature and the intermolecular forces. That we said it, we just drew it, and hopefully that kind of made sense. Okay, coming back to this slide for a minute. So this is what we just spent 5 minutes talking about. So one more time, the physical state of a substance depends on the balance of its temperature and the attractive forces between the molecules themselves. So when I heat iron, we got to heat it really hot to change it to a liquid. It has extremely high intermolecular forces in its metallic bond. I don't know, like a couple thousand degrees, should we ask? It's just really hot, vaporized iron that you wouldn't want to breathe. Hey Siri, what's the melting point of iron?
The melting point of iron
2800
is 2,800 degrees Fahrenheit.
So if you can get something that hot, then you'd have liquid iron. That's a lot. You know why? Because the iron atoms are super attracted to other iron atoms. And we would have to sever that major attraction between all of the iron atoms to get that to work. pretty cool. Okay. In general, as the intermolecular forces increase, the melting and boiling point increase. You have to be able to state that as fact on your test and answer why. Tell your partner why. So what do we think? The higher the intermolecular force, the greater the force of attraction, the more energy required to break that attraction. It's kind of a circular argument, but it is an important argument that AP is going to ask you to prove. You right with that? Okay. There are 3.5 types of intermolecular forces. You have to understand each one. And the reason one is called half, you'll see in a minute. It's hydrogen bonding, but hydrogen bonding is one of these. All right. So the first one we'll just discuss is an ion dipole force. Now, you're probably going to write stuff down, so you're going to be annoyed. But first, I need to define one more time. What is an ion? All right, it's a charged atom or molecule. So like K with a plus would be the potassium ion. Be all right with that? Okay, then it's an ion dipole. So we better discuss what we mean by a dipole. Any guesses? All right. 2 poles. Now, 2 poles, and that's good. It's like the S with the negative and the S with the positive. But this is supposed to be that Greek thing. But what you really care about is something that's dipole comes from a polar covalent substance. Did you getting it, Melissa? I just, those itches in the middle of the back, those are a pain.
It was really distracting me too.
Yeah, I'm like, get that, girl. Just come on. We've all been there, haven't we? Okay. Sorry, I made that awkward, I'm sure. Okay, so my friends, in order to have an ion dipole intermolecular force, you have to have 2 things present. Any guesses what they are? An ion and a polar substance. So, what can you think of any ion in the world?
Potassium.
There's one on the board. This is an ion right here, K plus, right? So in order to have an ion dipole reaction, I'd have to put this in a polar substance. What could we think of that's polar?
Water.
Water.
No way.
So when we have an ionic substance and a polar substance, we have ion dipole forces. this one's easy because it's just in the name. So what you'll be given is like a substance, and I will ask you what type of intermolecular forces exist in this substance. So if I told you that you had salt water, you would know I have ion dipole. But there's more. We're going to learn in salt water, it has every interaction. So you'd say all of them. But are we okay so far with ion dipole? Okay, I'll go back to this part. Ion dipole is exactly what it sounds like. It's an attraction between an ion and a polar molecule. A common example is salt in water. The polar water molecules are attracted to the sodium and chlorine ions. In red, these, so ion dipole forces, require a solution with an ionic substance dissolved in a polar substance. Let's see if I even have, oh, I do. All right. So this represents sodium chloride. Just as a review for a minute, tell your partner, green or blue, which one's the sodium and which one's the chlorine. Oh. There we go. Those are going to fall. Okay. So this mess right here. Oh, by the way, the green was which one? Green's the sodium. Because chlorine has really high Zeph. Remember? High Zeph, smaller molecule. Yeah, more electrons, but still way smaller. Okay. So here we go. This is an example of an ion dipole interaction. The green and the blue are the ions. And then the water, or the dipole, the polar water molecules, are the things that surround. The way that salt water dissolves is that you get all of these like attracted to each other, and they line up on one, and eventually you get enough of them to pull hard enough that they break the lattice structure down, and then it leaves. We call it being solvated. All right, we're going to learn that here in chapter 13. So we'd end up with just one of these chilling with all the whites lined up. And then you'd have, whoops, white, Tom. Then there's one more. Then you'd have just this sodium ion, and it would be attracted to the water molecules. And to break that separation, it would require me to pull, or it requires us to put energy in. So this salt water would have different physical properties than just pure water. Okay with that? And way different physical properties than just sodium chloride. So this is an example of a ion dipole. Okay, now I can also do the same thing here, but the blue is sticking to the red. How come? All right, so it's just, whoops, hey, that sticks both. There we go. All right, so maybe that wasn't a good example, but it would just offset and they pull each other apart. Thumbs up on that. All right, so next up, these aren't like very hard. We can cover chapter 11 if I had to in a single day. Now we won't, we'll take 2 or 3, but it's pretty simple. Yeah, we should test. It's the 19th I test on chapter 11 and 13 together because, as you all know, 11, 13 is very important to me. That's my birthday. We should be there by about the first week of February. So I started this chapter on the 16th last year. So we're like right there. Okay. Next are dipole forces. Once again, not really hard to understand as long as we just kind of read and know what dipoles are. So dipole is exactly what it sounds like. It's an attraction between two polar substances. Now, right here, don't think that they have to be different polar substances. It can be the same. Like it absolutely can be the same polar substance. So an example of that would be water molecules. What's that? Yep. Well, what'd you say? All right. So this would just be like water being attracted to water. Okay. So water has dipole forces. It also has hydrogen bonding, which is a form of dipole forces. So we'll kind of chop that up. All right. So in my solution right here, I don't just have ion dipole. I do have ion dipole because K is attracted to water, right? But inside this water, I also have water molecules that are attracted to other water molecules. So I would also say ion dipole and dipole and hydrogen bonding and London dispersion forces. It has everything. All right. So London dispersion forces, like they sound like someone just made them up. It's like you're full of crap. But hasn't chemistry felt that way all try? Like what? Did they just create this to make my life worse? There was once where it did?
Yeah.
Well, we got rid of that, hopefully. Okay, London dispersion forces are often just referred to as LDFs. Now, lately they've been asked to be called their full name, but I'm joking. I thought that was dang funny. The LDF would like to be called London dispersion forces. It's a sacrilegious joke, people. My goodness. Wow. How am I gonna infringe on your church and state freedoms if you don't even understand my sense of humor? Okay, here we go. Here we go. London dispersion forces are, there was nothing negative I said. London dispersion forces are forces created by induced dipoles in nonpolar substances. What?
That's so cute.
That was cute. Are we out of here at 1 or at 1:10? Oh my laws.
Are you dead serious?
So here you go. Here's a nonpolar substance, and here's a nonpolar substance. They can have an attraction to each other. The reason they can is because there is a chance that as this one moves closer to that one, it may repel the electrons away from it. And if those electrons are over here for a minute, that leaves this side positive and this side negative. And for just a moment in time, there's an attraction between that positive and negative. Now electrons move, so this will break, but as it's breaking, another induced dipole is formed, and we have what we call London dispersion forces, and you're great. I'll miss all of you. Yep.